Welcome to AI Paperslop. If you want the core insight of today's deep dive right this second, here it is. Human engineers are currently the primary bottleneck in autonomous AI improvement.
Right. They absolutely are.
Yeah, and until now, automated self-improvement research has been strictly split into two totally isolated camps. So in camp one, you have a meta agent that rewrites the external scaffold like prompts, tool dispatch, Python retry loops, but the model's internal weights are completely frozen.
Just totally locked down, yeah.
Exactly. And then in camp two, researchers use test time reinforcement learning to update the model's weights based on task feedback. But in that case, they strictly freeze the surrounding software scaffold.
Right, which is just as limiting.
It is. But today, we're unpacking a highly anticipated paper from Hexo Labs called SIA, Self-Improving AI with Harness and Weight Updates. And it finally bridges that structural gap.
It really does. It's a huge step forward.
It introduces SIA, an architecture where a central feedback agent analyzes full execution trajectories. And it dynamically chooses to update either the scaffold code or the model weights using LoRA.
Basically acting like a completely autonomous MLOps engineer.
Right. And the result? It just crushes previous state-of-the-art benchmarks across three wildly different technical domains. We're talking Chinese legal classification, low-level H100 GPU kernel optimization, and single-cell RNA denoising.
Yeah, and the most impressive part is that it does all of this entirely autonomously, like no human in the loop managing the RL pipelines at all.
Exactly. So our mission for you today is to unpack exactly how this dual lever system works in practice. We're going to look at the specific RL algorithms the agent dynamically selects, and we want to explore why changing the weights unlocks a type of internalized domain intuition that no amount of prompt engineering can ever achieve.
Yeah, and to really appreciate why SIA is such a breakthrough, we first need to understand the structural flaw in how the ML community has been approaching self-improvement for the last couple of years.
Right, the two camps thing.
Exactly. We've essentially been running two parallel races that just refuse to look at each other.
So let's look at that first track, the harness or scaffold silo.
Yeah.
This is where you find systems like the Darwin-Gödel machine or meta harness, right? And from what I understand, these approaches heavily rely on iterative refinement, but strictly at the prompt and code level.
Exactly. So in this approach, you use a highly capable LLM as a meta agent, and its entire job is to just mutate the system prompts, the tool dispatch logic, and the parsers of a separate task-specific agent.
Okay.
Over multiple generations, it evaluates which prompts get the highest score, mutates the winners, and basically writes better and better Python code to manage the task.
Right. So it's like putting a world-class project manager in front of a junior developer.
Right.
Like the developer doesn't actually get any smarter, but the manager sets up perfect JIRA tickets, writes incredible documentation.
Builds better error catching, yeah.
Exactly. You're getting pristine software engineering hygiene.
That's a great way to put it, actually. You get better retry loops and cleaner API calls. But here is the critical limitation, right? The underlying language model's weights remain completely fixed.
Right. The engine doesn't change.
Exactly. That hygiene is incredibly valuable, but it rarely surfaces any deep domain reasoning that the base model didn't already have buried inside it. It's just organizing the existing knowledge more efficiently.
Okay. And then on the other side of the campus, completely isolated, we have the test time post-training silo.
Yes. So this is your TTRL or the Discover line of test time training. Here, researchers write a fixed reinforcement learning pipeline.
Okay.
The model attempts a task, the environment provides a reward, and that reward is used to update the model's actual internal weights.
So the model is genuinely learning there, like its internal policy is fundamentally changing.
It is, yeah. But the catch is the scaffold.
Ah, right. It's rigid.
Completely rigid. The pipeline is engineered by humans. It uses a single fixed prompt and grader template. It does not adapt the surrounding software scaffold to the specific structure of the task as it learns.
So it really is like trying to build an autonomous race car where you've got two teams, like one team is only allowed to upgrade the steering wheel and the dashboard, that's the harness team.
Right.
And the other team is only allowed to tune the physical engine, that's the weights team. And for some bizarre reason, they are strictly forbidden from speaking to each other.
It sounds absurd when you put it like that.
It does. I mean, looking at it from an engineering perspective, why hasn't anyone just put them in the same room before this paper? It seems so obvious.
Well, it sounds obvious in hindsight, sure, but combining them is a massive infrastructural nightmare. Think about the tooling required for a second.
Okay.
Updating a Python script involves string manipulation, execution environments, unit tests. but updating model weights in a closed loop.
Oh, right. Gradients.
Exactly. You're orchestrating distributed RL gradients over low-rank adapters, you're managing optimizer states, handling hardware memory constraints. The NLP prompt engineers and the MLOps reinforcement learning engineers have basically been living in different universes.
With entirely different tool sets.
Exactly.
Well, until Hexo Labs decided to force them into the same pipeline. So let's deconstruct how they actually built this SIA architecture.
Yeah.
Because orchestrating this autonomously is no small feat.
No, it's not. They broke the system down into 3 distinct LLM components to separate the concerns. First, you have the meta agent, and they use Claude Sonnet 4.6 for this role.
Okay, Sonnet 4.6.
Yeah. Its only job is to initialize the very first starting scaffold based on the task specification and the verifier. It reads what the benchmark is testing, and it writes the initial Python dispatch code and the baseline prompts.
Right, so that's the setup. Then you have the worker bee, like the model actually sweating over the test.
Right, the task-specific agent. For this, they use an open-source model, GPT-OGOS-120B. This is the agent actually executing the code, trying to solve the benchmark, and generating what they call a trajectory.
Let's actually define trajectory here for you listening, because the entire feedback agent relies on it. We're not just talking about the final output string, right?
Oh, not at all. The trajectory is the complete structured execution log.
Everything.
Everything. Every single prompt it received, every tool call it made, the exact API responses, every Python syntax error it threw, and the final extracted answer. It is the full context of the attempt.
Wow. Which gets fed into the third component, right? The brains of the operation. The feedback agent.
Yes, also powered by Claude Sonnet 4.6.
Right. And it reads that entire massive trajectory log to diagnose exactly why the task-specific agent failed.
Yeah.
And I want to pause here because this dynamic is what makes the paper so compelling to me.
It's the core of the whole thing.
Yeah. We have a Claude model analyzing a log, and it
Yeah.
has to actively decide, do I rewrite the Python parser, a harness update, or do I trigger an RL pipeline to adjust a LoRA adapter on the GPT model await update?
Yeah. Like, how does it actually make that choice? Is there just a hard-coded threshold or something?
It's not a simple threshold at all. It's an active diagnosis. The Claude model is acting as an autonomous MLOps engineer.
Okay.
So if it looks at the log and sees that the GPT model correctly reasoned through a math problem, but, say, failed to format the output as a JSON object, it knows the weights are fine.
Oh, because the logic was there.
Exactly. The model understands the math. The scaffold just needs a better parser. But if the GPT model outputs perfectly formatted JSON, but the internal logic of the answer is completely fundamentally flawed.
Then the code is fine, but the model is dumb.
Right. The feedback agent realizes the model itself simply doesn't understand the domain, and that's when it pulls the weight lever.
And this is where it diverges from just running a generic script. When it pulls that weight lever, it dynamically selects the specific RL algorithm based on the task environment.
Yes.
Let's see how that plays out in practice.
Yeah.
Because they tested some wild domains. They really did. The first major domain they tested was LawBench, which is just a brutal data set. Specifically, they used a 191 class Chinese criminal charge classification task.
Okay, so the model reads a factual summary of a case and has to identify the precise criminal charge. And looking at the benchmark, we are talking about incredibly fine legal distinctions here.
Very fine.
Like, it's not just did they steal something. The model has to distinguish between ordinary theft, public property theft, and embezzlement, or between, simple assault, aggravated assault, and grievous bodily harm. These are legally precise statutory differences.
Exactly. So they set SIA loose on it. Initially, the system defaults to harness updates. The Claude feedback agent iterates on the Python code and quickly realizes it needs context.
Right.
So it builds a TF-IDF and linear SVC pipeline to re-rank the model's top legal candidates.
Just for a quick refresher for everyone, TF-IDF is term frequency inverse document frequency. So basically a statistical measure to evaluate how important a word is to a document. And linear SVC is a support vector classifier. So the harness is basically building a classical machine learning pipeline to act as a retrieval assistant for the LLM.
Yeah, exactly. It tunes the Enneagram ranges, it writes better parsing logic, and the accuracy jumps massively from a baseline of 13.5% up to exactly 50.0%.
That's a huge jump.
It is, but then it stalls. It hits a hard plateau.
Because the software hygiene can only take you so far. right? Like you can give the model a perfectly formatted prompt with the best re-rank statutes, but if it fundamentally doesn't grasp the nuanced legal difference between two variants of assault, it's just guessing.
Precisely. The feedback agent detects this stalled reward and makes the decision to switch to a weight update.
Okay, here we go.
And because the reward signal here is a clean, outcome-based scalar, meaning you either predicted the correct legal charge or you didn't, the agent dynamically selects PPO with GAE.
Okay, wait, I want to challenge this a bit. PPO with GAE, proximal policy optimization with generalized advantage estimation. Why that specific algorithm? Like, why not just use standard gradient descent or a simpler RL setup?
It's a good question. It's because of catastrophic forgetting.
Yeah.
When your step-level rewards are dense and clean, your biggest constraint is training stability. If you do a massive unconstrained weight update on a complex 120 billion parameter model while trying to teach it complex reasoning, you risk collapsing the model's policy entirely.
It might, like, memorize the Chinese legal code, but totally forget how to formulate a coherent English sentence.
Exactly.
So PPO keeps the guardrails up.
Yep. PPO uses a learned value head to estimate the advantage of every single token the model generates, and GAE helps reduce the variance of those estimates. Then PPO applies a clipped surrogate objective.
That means
That clipping ensures the policy doesn't drift too far from the original working baseline in any single update step. It applies a very stable, controlled gradient pressure.
And the result of that stable pressure is that the accuracy skyrocketed to 70.1%.
Incredible, right?
It absolutely crushes the previous state-of-the-art, which was only 45.0%.
But the why is what you really need to take away from this. The harness updates plateaued because you cannot prompt a model into having a law degree.
No, you really can't.
The PPO weight updates physically altered the model's internal parameters to build internalized domain intuition. It learned the statutory law through the physical pressure of gradient descent.
Which is actually a perfect contrast to their next test. Because LawBench gave the system a very clean, dense reward. You got it right or wrong. But what happens when the task is brutal, low-level systems engineering, where almost every single attempt is a complete failure?
Yeah. That's the perfect transition to their next test, AlphaEvolve Trimal. The task here is writing a custom CUA kernel for a triangulating multiplicative update.
Right.
Which is an operation heavily used in AlphaFold 2 for protein structure prediction. And they are running it on an NVIDIA H100 GPU. And this is notoriously difficult because it is not compute limited, it is memory bandwidth limited.
Okay.
Because of the triangular sparsity structure of the data, the GPU threads have to access non-contiguous memory. This creates warp divergence, where threads in the same execution group get out of sync and severe cache misses.
So standard stuff won't work.
It totally defeats standard human-written libraries like Couplase. You have to write highly optimized custom C++ and CDA code to make it fast.
So SIA starts with harness updates again.
It does what a good software engineer would do. It sees compilation errors, so it builds compilation error parsers to feed those exact syntax errors back into the context, and it builds retry loops.
Right.
This software hygiene ekes out a 1.14 times speedup, dropping the runtime to about 12,480 microseconds. But again, it hits a plateau.
The dashboard and the steering wheel are fully upgraded. It's time to tune the engine.
Exactly.
So the feedback agent switches to weight updates. But earlier you said it uses PPO for dense rewards. If it uses PPO here, it's going to fail, right?
Oh, it would fail completely. When you are writing low-level CUDA kernels, most of the generated code simply fails to compile. A missing semicolon or a memory allocation error means the runtime is 0.
So the reward is 0.
Exactly.
So if you use standard RL gradients from a cold start, you are literally just multiplying by 0. The reward signal is incredibly sparse.
Extremely sparse. So the feedback agent dynamically pivots to a completely different algorithm. Entropic advantage weighting.
Okay, break that down for us.
Right.
How does that solve the sparse reward problem?
Well, entropic advantage weighting is specifically used when the reward histogram is heavily right-skewed, meaning most rollouts are absolute trash, but a rare few are high signal.
Okay.
Instead of zeroing out the bad rollouts and getting stuck, the algorithm uses a softmax function with an adaptive temperature to massively upweight the rare high-reward rollouts and redistributes the gradient mass to just ignore the noise.
Okay, so it's actively hunting for the, 1 in 100 times the code actually compiled and ran a tiny bit faster.
Right.
And it disproportionately amplifies that specific trajectory, basically screaming at the model, do more of that.
Yes, exactly. And the adaptive temperature is crucial because it ensures that the effective sample size stays above a floor threshold.
Which prevents overfitting.
Exactly. It prevents the model from collapsing onto a single mediocre trajectory and overfitting.
And the results here are staggering. It dropped the runtime to 1,017 microseconds.
Yeah.
That is a 14.02 times speed up.
Huge.
It easily beat the previous SOTA of 1,161 microseconds. But I want to make sure you and I are tracking the actual mechanism here, because the model didn't just learn to avoid syntax errors.
No, the RL updates physically rewired its weights to fundamentally understand H100 hardware architecture.
Wow.
Through those gradients, the model internalized incredibly complex design patterns like shared memory tiling and FP32 register accumulation that standard libraries don't even use for this operation. It built a hardware intuition that the textual scaffold could never, ever reach.
That is just wild. It literally learned the physical realities of the silicon it was running on.
It did, which leads us perfectly to the final domain, which is biological data, magic cRNA-seq denoising. And this one reveals the most surprising emergent behavior in the entire paper.
Okay, let's set the stage here. Single-cell RNA sequencing matrices are highly sparse. You have a lot of missing signals due to technical dropouts.
Right.
Meaning the sequencing machine physically fails to capture some of the RNA molecules that are actually present in the cell. The magic algorithm, which stands for Markov affinity-based graph imputation of cells, imputes or mathematically fills in that missing signal.
Right. But you have to tune magic's hyperparameters for it to work. You know, the number of neighbors, the diffusion steps, the kernel bandwidth.
And it's a very delicate balance, right?
Very. If you set the neighbors too low, you overfit to technical noise. If you set it too high, you oversmooth and destroy the true biological signal.
So the harness goes to work.
Yep. The scaffold iterations successfully build a batched configuration driver. It sweeps the hyperparameter space, testing different combinations, and plateaus at a normalized mean-squared error insinorm of 0.241. And higher is better here.
And once again, the Cloud MLOps engineer steps in. Time for a weight update. But I'm guessing it doesn't use PPO or entropic weighting this time?
No, it switches to GRPO, or Group Relative Policy Optimization.
Hold on, why GRPO specifically here? Like, why couldn't it just use the entropic weighting you mentioned a minute ago?
It basically comes down to the cost of the environment. In this task, rollouts are incredibly cheap to sample and evaluate in parallel. You can run hundreds of hyperparameter tests simultaneously.
Oh, I see.
GRPO eliminates the value network entirely. It just normalizes the advantages within a group of rollouts sampled from the same prompt. This halves the memory requirement and lets you run massive parallel batches.
Okay, here's where it gets really interesting. The aha moment of the paper. What did the model actually do during this weight update? Because it wasn't just guessing better hyperparameters.
No, it completely abandoned parameter tuning. The weight update generated a structural transformation that the scaffold-only loop never even considered.
What did it do?
It physically inserted a two-line Python post-processing step into the code, np.clip followed by np.rint.
Wait, let me make sure I'm understanding this. It added NumPy code to round the imputed RNA counts to non-negative integers.
Yes, it did exactly that.
Wait, so you're telling me no human put a rule in the prompt about RNA molecules being whole numbers? The math itself figured out biological physics.
Exactly. It realized, purely through the pressure of gradient descent, that you cannot have a fraction of an RNA molecule. It enforced a biological invariant.
That is insane.
A constraint that is trivially obvious to a human biologist, but was completely absent from every version of the prompt and the scaffold. The gradient pressure pushed the policy to understand the biological physical reality of the data.
I just want you to sit with that for a second. The model learned that you can't have half a molecule. Not because a human told it, and not because it read a textbook in its prompt, but because the math of the reinforcement learning update forced its weights to recognize reality.
Yeah.
And that single realization pushed the score to 0.289, comfortably beating the previous SOTA of 0.240.
It's amazing. And if we connect this to the bigger picture, looking at all three of these benchmarks, a very clear philosophical difference emerges regarding what these two levers actually accomplish.
Right, let's synthesize this. We're basically looking at external hygiene versus internal knowledge.
Exactly. Harness updates provide externalized changes. They give you the songware hygiene, the parsers, the search procedures, the retry loops. It shapes how the agent interacts with its environment.
But weight updates provide internalized knowledge.
Yes. They build the domain priors, the hardware architecture constraints, the biological invariants.
And the genius of SIA is that the feedback agent maps the RL algorithm perfectly to the environment, like PPO when it needs stability, GRPO when rollouts are cheap and parallel, entropic waiting for sparse rewards. It's a fully dynamic MLOps pipeline.
It is.
But I know there's a catch. The authors note a primary limitation in the paper, the coupled Goodhart trap. And I want to unpack this because it feels really important for anyone deploying these models. Goodhart's law says that when a measure becomes a target, it ceases to be a good measure. How does that apply to SIA?
Well, think about what is happening under the hood. In SIA, both the harness and the weights are co-evolving, but they are co-evolving to optimize against the exact same fixed verifier.
Oh, I see. The grader at the end of the benchmark test never actually changes.
Exactly. Because they are both optimizing against the same grader, they are at high risk of falling into a coupled Nash equilibrium. The harness might just be finding scaffolds that are incredibly easy for the current weights to exploit. Rather than scaffolds that are actually robust, they might just be finding highly brittle exploits specific to that exact verifier.
Rather than achieving generalized, robust improvement.
Right.
So let me see if I have this right. They are basically just conspiring together to cheat the test rather than actually learning the material. Like a student and a tutor figuring out a trick to pass a specific multiple choice exam. But if you change the format of the questions even slightly, they both fail completely.
That is a perfect analogy, yes. When two optimizers are blind to each other's update history but share the same rigid goal, the fixed points they reach can be incredibly fragile if you introduce even a slight perturbation to the real-world environment.
That makes total sense. So what does this all mean for you, the listener, who is actively building these systems? I want to leave you with a final provocative thought directly from the future work section of this paper. Right now, the feedback agent uses a frozen prior Claude Sonnet 4.6 to decide whether to pull the harness lever or the weight lever. It's using its pre-trained intuition to act as the MLOps engineer.
But it's static. The selector itself isn't learning from its mistake.
Exactly. But what if we run meta-RL on the selection policy itself? Imagine an outer loop where the system actually learns how to learn.
Wow.
The AI wouldn't just be improving its Python code and tuning its weights. It would actively be upgrading its own intuition about which self-improvement strategy to use in any given moment. It would learn from experience that, hey, on sparse reward tasks, I should trigger entropic weighting sooner.
It becomes a genuinely recursive structure. The improvement mechanism itself becomes self-improving.
Right. If the steering wheel team and the engine team are finally talking to each other, what happens when the manager coordinating them can artificially evolve to become the greatest project manager in history? Where does the ceiling of self-improvement sit when the improvement mechanism itself becomes self-improving? That's something for you to chew on today.
It is a fascinating horizon.
Keep pushing the boundaries of your own learning. Thanks for joining us, and we'll see you next time on AI Paper Slop.